everyone, our topic for today is about multiple integrals. So in this lesson, we will learn how to evaluate multiple integrals um, like double and triple integral. So the objective of this lesson is you should be able to evaluate multiple integrals. So let me first define what a multiple integral is. When you say multiple integral or iterated integral, it is the result of applying integrals to a function of more than one variable in a way that each of the integrals considers some of the variables as given constants. So there are two types of multiple integrals. The first one is called the iterated integrals with constant limits of integration. And the second one is the iterated integrals with the non-constant limits of integration. So under this type of multiple integral, so given the function f of xy, which is a continuous on a rectangular region R of length from a to b and width from c to d. Then the double integral of f of xy times the change in the area over this rectangular region R is equal to the double integral of f of xy dy dx, where y is from c to d and x is from a to b. So as you can see, the order of integration is first with respect to y and then second is with respect to x. So the inner limits is for the y variable and the outer limits is for the x variable. Okay, this double integral can also be defined as the double integral of f of xy dx dy, where x is from a to b and y is from c to d. So look at the order of the coefficient of f of xy, such as dx and dy. So dx comes first or written first before dy, and because dx is written first, so the inner limits is for the x variable and the outer limits is for the y variable. So to evaluate the double integral of f of xy with this order, dy comes first before dx, you have to evaluate the function, or you have to evaluate the integral of the function f of xy first with respect to y, where y is from c to d. And then the resulting integral will be integrated for the second time, but with respect to x, where x is from a to b. Okay, so similarly, using the second definition of the multiple integral, wherein you have the double integral of f of xy dx dy, where x is from a to b and y is from c to d. And as you can see, since the order of integration is dx first followed by dy, where so this indicates that we have to evaluate the integral of this function first with respect to x and then second is with respect to y. So if this function is evaluated first with respect to x, where x is from a to b, the resulting integral will now be integrated this time with respect to y, where y is from c to d. So these two definitions are the double integral of the function with the order dy dx in the first double integral, and then dx dy in the second integral. And take note that to evaluate the double integral of this function, the region must be a rectangular region. Okay, the second type of multiple integral is the iterated integrals with non-constant limits of integration. So, as I said, for iterated integral with non-constant limits of integration, the region or the bounded region is non-rectangular. So this is double integrals over non-rectangular regions, and this can be evaluated by using any of the following types. If the order of integration is dy dx, then the inner limits are functional limits. The lower limit is g sub 1 of x and the upper limit is g sub 2 of x. So you have to evaluate this function f of xy first with respect to y, where y is from g sub 1 of x to g sub 2 of x. So you get this. And then after that, we will evaluate the resulting integral second with respect to x, where x is from a to b. So as you can see, because the region because the region is non-rectangular, the inner limits are functional limits and the outer limits are constant limits. Okay, on the other hand, if the order of integration is dx dy, then we have to evaluate this function, the integral of this function, first with respect to x and then followed by the integral of the resulting function with respect to y. So as you can see, because the bounded region is non-rectangular, so the inner limits are functional limits, while the outer limits are constant limits. So to evaluate the double integral of this function with this order, so we have to evaluate the integral of this function f of xy with respect to x, where x is from h sub 1 of y to h sub 2 of y. And then after that, we will evaluate the resulting function with respect to y, where y is from c to d. Okay, so that's the difference between the iterated integrals with constant limits of integration and iterated integrals with non-constant limits of integration. Okay, next we have the properties of double integrals. So the first property of the double integral is that number one, the double integral of the constant times the function f of xy times the change in the area over this rectangular region R is also equal to c. You factor out c because c is constant, and then multiplied by the integral of the function f of xy times the change in the area over this rectangular R. So as I said, take note that c here is a constant. And f of xy is a function of two variables, x and y. So this is the equation of the surface. Next, number 2, the double integral of f of xy plus g of xy times the change in the area over this rectangular region R is equal to the sum of the double integral of each function. So you have the double integral of f of xy times the change in the area over this rectangular region R plus the double integral of g of xy times the change in the area over this rectangular region R. So this indicates that the double integral of the sum of the two function with respect to times the change in the area over this rectangular region R is equal to the sum of the double integral of the first function times the change in the area of over this rectangular region R plus the double integral of the second function g of xy times the change in the area over this rectangular region R. Okay, the third property is that the difference or the double integral of the difference of these two functions f of xy and g of xy times the change in the area over this rectangular region R is equal to the difference of the double integral of each function. So you have the double integral of f of xy times the change in the area over this rectangular region R minus the double integral of g of xy times the change in the area over this rectangular region R. Okay, so as an example, suppose we are asked to evaluate the double integral of 20 minus xy times dy dx. Now, where y is from 2 to 4 and x is from 1 to 3. So, to evaluate this double integral, because the order of integration is dy dx, meaning we have to integrate the function first with respect to y and then later on with respect to x. So integrating the function with respect to y, treating x as constant. So when you get the integral of 20 dy, so you have 20y. Okay, and then when you get the integral of xy dy, treating x as constant, so you factor out x, and then you integrate y dy. Recall that the integral of y dy is y squared over 2, where y here is from 2 to 4, where 2 is the lower limit, 4 is the upper limit. So by substitution, because the upper limit is 4, so 20 times 4, so we got 80 minus x times, because the upper limit is 4. So you have, by substitution, 4 squared is 16, divided by 2 is 8, times x, so you have 8x. Minus, if y is 2, then 20 times 2 is 40, minus, factor out x, and then substitute the value of y, which is 2. So 2 squared is 4, divided by 2 is 2, times x is this one, negative 2x, multiplied by dx. And then simplifying further, um, you subtract 80 by 40. So 80 minus 40, you get 40. And negative 8x minus minus. So negative negative, this becomes positive 2x. And negative 8x plus 2x, you get negative 6x times dx. Where x here is from 1 to 3. And then by integrating this function with respect to x, you get 40. What is the integral of 40 dx? The integral of dx is x. So you have 40x minus, you factor out 6 and then get the integral of x dx, which is x squared over 2. But x squared over 2 times 6, you get 3. So 3x squared. Okay, where x is from 1 to 3. So 1 is the lower limit, 3 is the upper limit. Then by substitution, substitute. So 40 times 3, you get 120 minus. So this is 3 squared is 9 times 3, so 27. Minus, because the lower limit is 1, so by substitution, 40 times 1, you get 40. Minus 3 times, because the value of x is 1, so 1 squared is 1, times 3, so you get negative 3. But 120 minus 27 minus, you remove the symbols of grouping. So 120 minus 27, so you get 93 minus, but 40 minus 3, this is 37. Okay. So 93 minus 37. So you get 56. So this indicates that the double integral of 20 minus xy dy dx, where y is from 2 to 4 and x is from 1 to 3, is equal to 56. So in summary, to evaluate the double integral, you have to consider whether the region is rectangular or non-rectangular region. So for rectangular region, to evaluate the double integral, you have the order of integration is either dy dx or dx dy. So for double integral of f of xy times the change in the area over region R, if the region is rectangular, then this can be evaluated by evaluating the double integral of the function f of xy dy dx, where y is from c to d and x is from a to b. So take note that if the order of integration is dy dx, then you have to integrate this function first with respect to y and then with respect to x. But this is also the same thing as double integral of f of xy times dx dy, where x is from a to b and y is from c to d. Again, because the order of integration is dx dy, then we have to integrate the function f of xy first with respect to x and then with respect to y. For non-rectangular region, the double integral of f of xy times the change in the area can be evaluated using this order, dy dx or dx dy. So it depends on whether the function is bounded left and right by two curves or above and below by two curves. So if the region is bounded, let's say above and below by the two lines y equals g sub 1 of x and y sub 2 equals g sub 2 of x, then the order of integration should be dy dx. So this can be evaluated by taking the double integral of f of xy dy dx, where y is from g sub 1 of x to g sub 2 of x, and x is from a to b. But if the region is enclosed left and right by two curves, by the first curve, x equals g sub 1, h sub 1 of y, and x sub 2 equals h sub 2 of y, then the order of integration should be dx dy. So this can now be evaluated by taking the double integral of f of xy dx dy, where x is from h sub 1 of y to h sub 2 of y, and y is from c to d.